In this lesson, once we've created a scatter plot and drawn a line of best fit, we want to use that information to make predictions. So this lesson is about using models to make predictions. So for example, we have a table of values here where the speed of sound is related to the speed of a plane or an aircraft. So sound travels at a speed of 1,200 kilometers per hour. When it breaks the sound barrier, it is flying at the speed of sound, and this is called Mach 1. So Mach 1 is 1,200 kilometers per hour, Mach 2 would be 2,400 kilometers per hour, and Mach 3 would be 3,600 kilometers per hour. So we can take these points. This is my x variable, and this is my y variable. So the Mach number is the independent, and the speed is the dependent variable. And we're going to plot these onto a graph. So here's my graph. So I can see that the x-axis is the Mach number and the y-axis is the speed in kilometers per hour. So make sure you label your axes and you put units if that is appropriate. So once we've plotted the points and we've drawn our line of best fit, this is continuous data. So we have drawn a line because there are possible points in between these points. We could have Mach number 1.5, we could have Mach number 3.8, and so on. So we've drawn a line. This is the information that we're given, and we've connected the points. And now we want to use the graph to estimate the Mach number at 1,500 kilometers per hour. So what we do is we find 1,500 kilometers on the y-axis. This is the speed. So you can see since 3 squares is 1,200, each square is an increment of 400 kilometers per hour. This would be 800, then we have 1,200, then we have 1,600. So 1,500 is approximately here. We go over to the line and then we go straight down to read off the Mach number. So remember, on graphs it is an approximation. I cannot be exact with a graph, but I can approximate. So I'm going to put approximately, and it looks like it's approximately Mach number, I'll say 1.25. 1.5 would be halfway in between 1 and 2, and then this looks like it's about halfway between that. So I'm going to approximate it at 1.25. I can also use the graph the other way to estimate the speed if I had the Mach number. So the Mach number is 2.5. So estimate the speed. So I'm going up. Let's draw the arrow the other way. So I'm starting at 2.5 at the Mach number. I'm going up to the graph, and then I'm going straight across at a right angle to read off the speed. Looks like it's approximately 3,000 kilometers per hour. So if I use the graph to estimate values that are within the data set, this is called interpolation. Back to the graph. Mach 4 is not included on this information I was given. So I would need to make this line longer to estimate Mach 4. So once I make it longer, then I could go Mach 4, I could go up to here, and then I could go across to estimate where that might be. So these are 400, so that's 4,000, 4,400. So I'd say it's approximately 4,800 kilometers. Either direction. So if I wanted to do 900, I'd have to make the line longer this way, and then 900's approximately there. Go straight down, and you'll notice I'm putting arrows to show the direction that I'm going. So I'm starting at 900, I'm going to the line, and then I'm going down. So I'm putting arrows on it to show which direction I'm going. And it looks like it was approximately, it was less than 1, but bigger than 0.5. So interpolation means that I used the data set that I had, and I was able to estimate the data within the points that I had. If I want to use the graph to estimate points beyond the data set, beyond the information given, and I have to make the line longer, so we're going to make it extra long. This is called extrapolation. So you see the word extra? That means I'm going to make the line extra long in either direction to find the answer. And so if I want to use the graph to estimate the speed at Mach 4 per hour, So at mark 4, I had to make the line longer, so that's extrapolation. You see the word extra in there. And then I was able to find that information by making the line longer. I can make the line longer. It is approximately, let's see, we want the Mach number, so put about 0.6. Is approximately where it is. So when you are using your line of best fit, you are estimating your answers. It's not exact, but it is a good estimation. So here we have a hot tub, and when they want to do maintenance on the hot tub, they have to add chlorine. And so the x-axis is measuring the volume of the hot tub. That is my independent variable. You can see that because they're really big numbers, they just put 1, 2, 3, 4, but then in brackets they've put thousands of liters. So that means 1 is 1,000 liters, 2 is 2,000 liters, and so on. So sometimes we do that if we don't want to put big numbers on the axes. We can say we'll just do 1, 2, 3, 4, but each one is representing times 1,000. And then on the y-axis is the amount of chlorine in grams that they are putting in the hot tub. So we want to determine the volume of water in the hot tub that requires 10 kilograms of chlorine. So I'm going to find 10 kilograms or grams. I'm going to go over to my line of best fit. I'm going to go down, put the arrows to indicate which direction I'm going in, and it looks like it's about 2.5. Remember, it's in thousands, so I'll put 2,500. So we'll put 2.5 or 2,500 liters of water. We can go the other way, determine the mass of chlorine needed for 500. So 500 is approximately here, which would be 0.5. I'm going to go over here, indicate the direction I'm going. So looks like it's between 5 and 0, so I'll put approximately 2.5 grams of chlorine. And this was water. Okay, so we are using the graph to determine that. 3,000 liters would be here. I'm going up to the graph, and I'm going across to find that grams of chlorine. It's between 10 and 15, so I'm going to say approximately 12.5 grams of chlorine. So I'm indicating my answer in units and what I'm measuring. And then volume of water, that would be 17. 17 is between 15 and 20, so probably about here. And so it looks like it's 4 and a bit. So I'm going to say approximately 4.5 or 4,500 liters of water. So I was able to find most of this information within the data set. Perhaps the 500 liters, I had to make the line a little bit longer, but I was able to find that from there. Okay, here we have a table that is indicating distance traveled by a car that is traveling at a speed of 100 kilometers per hour. So it wants me to plot the points on the graph and then use that information to answer these questions. So first thing I want to do is label my axes. So let's do this in black. So the x-axis is measuring time. So we'll put this on the x-axis and we'll indicate the units. The y-axis is measuring distance. So we'll put that there in kilometers. I'm going to start at 0. I'm going to make every 2 squares 1 hour just to spread out the information. And then on the y-axis, I'm going to make every 2 squares 100 kilometers, again, just to spread out the information so I'm not squishing everything into a small area, and it is easier to read. And then we will plot the points. So at 1 hour, it traveled 100 kilometers, so I go right 1, up 100. At 2 hours, it traveled 200, so I go right 2 hours up to 200 kilometers. At 3 hours, it traveled 300 kilometers, and at 4 hours, it traveled 400 kilometers. Am I going to join the line? Yes, I am. It is continuous data. I could have time in between hours. So I could have 1.5 hours, I could have 2.4 hours, and so on. So I am going to draw a line between the points to show that there could be points in between. Okay, now we're going to use our graph to find the distance traveled at 1.25 hours. You'll notice that it says interpolation because we do have that information on the line that we drew. So 1.25 is approximately here, and then I'm going to go over to find that distance. So it's approximately 125 kilometers. And then again, I'm going to use interpolation to find 225 because that information is within the line given. So here's approximately 225, and we'll go down to find that information on the grid, and it looks like it is approximately 2.25 hours. And then it indicates to use extrapolation to find 80 kilometers. That's because I need to make the line a little bit longer to find 80. So I'm going to extend the line this way. And then I'm going to do 80, which is about here, and go down, indicating the direction. So it's approximately 0.8 hours. And then 5.5, I'd have to make the line longer this way. And we'll do 5.5 hours, which is here. And then go across. And it looks like it's approximately 5.25 or 525, I should say. Now remember, it's not exact. Probably should be about 550 kilometers, but from my drawing, it's about 525. So it's not exact, but it is an approximation. So in that case, we used extrapolation because we had to make the line longer the other way. Okay, we can also get an equation, and then in Unit 12-13, we're going to start looking at how do we find that equation. But one way to find an equation for our line of best fit is to use Desmos. So what I've done is I've put this table of values. X in the is the independent variable temperature, and Y is the number of chirps. So these are crickets that are chirping, and as the temperature fluctuates, we can measure how many times they chirp. So it looks like as the temperature, which is on the x-axis, and it is in Fahrenheit, not in Celsius. As the temperature increases, it looks like the number of chirps we hear also increases. So it is a positive correlation. So there is a relationship, and it is a positive one, meaning that as x increases, y increases. So I used Desmos to plot that table of data, and then I estimated the line of best fit. So I just looked at some numbers and looked at the line that would best fit that data. So my equation that I found as my line of best fit, it was x minus 35.5. And there is some information in the guide on how to estimate your line of best fit. So basically I'm looking at the relationship between x and y, and I want to change the variables so I can move that line up and down and try to find the line that best goes through those points. Once I have 90 degrees Fahrenheit, let's see, that's 20, 40, 60, 80, so 90 is about here, and I'm going to approximate over to here. And what's that? 20, 40, 60. So it looks like it's about 57.5. So let's go 28 chirps. So chirps is up here. So 20, 30. So 28's about here. And I'll go straight down. So it looks like it's approximate temperature of 20, 40, 60. So I'm going to say 65, my line of best fit. So the equation was y equals x minus 35.5. I can predict either from the graph or from my equation. So from the graph, it wants me to find the number of chirps when a temperature is 90 degrees Fahrenheit. So from the graph, I'm going to go to the graph. Probably from my graph, so I'm going to say approximately 57.5 chirps. That's from my graph. So that is an approximation. From the equation, I found an equation from my line of best fit as y equals x minus 35.5. So I'm going to put in x has a value of 90 degrees Fahrenheit. So put in 90 minus 35.5, and that gives me an answer of 54.5 chirps. So you can see the answers are a little bit different, but pretty close. So from the graph, it was 57.5 approximately. From my equation, which is going to be a little bit more accurate, it was 54.5. Okay, in 2, it wants me to find the temperature when we hear 28 chirps. So again, I'm going to look at the graph. So from the graph, look at the approximate number, 28 chirps approximately. Approximate temperature would be 65 Fahrenheit. And then we'll also do that calculation from the equation. So the equation was x minus 35.5. This time we have the number of chirps, which is the final value. So 28. So if I want to solve for x, I would have to do the opposite. So instead of subtracting 35.5, I would have to add. Remember, we did solving in a previous lesson. And so x will be, so that's 0. So 28 plus 35.5 is 63.5. So again, close. This one was 65 from the graph, and from the equation it was 63.5. So my graph is not always an exact science. The equation is more accurate. And in Unit 12-13, we are going to start to look at, well, how do we find that equation of that line? How do we find the rate of change and the starting amount?